Hello and welcome! Today we're jumping into a fascinating field designed to solve some pretty impossible-sounding problems: unsupervised machine learning. Think of it as a guide for engineers to teach machines how to find the things we don't even know we're looking for.
So let's just kick things off with a huge question. Imagine you're in charge of cybersecurity. Your whole job is to stop hackers. But how on earth do you defend against an attack method that literally no one has ever seen before? How do you describe something that's completely new?
Well, that's the whole challenge with what we call zero-day attacks. Most security systems, they're basically like a bouncer at a club with a list of known troublemakers. If your name's on the list, you're not getting in. But what if a brand new threat shows up, someone not on the list? They can just waltz right past. This is where the old rulebook just completely falls apart.
To solve a problem like that, you really need a totally different way of thinking, a paradigm shift. You need a system that can learn without a teacher, one that can spot trouble without needing a pre-written list of what trouble even is. And that is exactly what unsupervised learning is all about.
Okay, so let's get the formal definition out of the way. Unsupervised learning is a type of machine learning that works with unlabeled data. And that's the key phrase right there, unlabeled data. There's no answer key provided. The model is thrown into the deep end and has to figure out the hidden structures and relationships all by itself.
What's so cool about this is just how human it feels. Just picture this. You're dropped into a totally new environment, filled with bizarre creatures you've never seen. You don't have a field guide. But what do you do instinctively? You start sorting. You'd go, okay, all of these things have long trunks, and these over here have sharp horns. You're creating order out of chaos, finding patterns without anyone telling you what to look for. That's the core idea.
And this really highlights the big difference between the two main types of machine learning. See, supervised learning, that's like studying for a test with flashcards. You've got the question on one side and the right answer on the back. It has a teacher. But unsupervised learning, that's like being an explorer. You're given a map of a new world, raw data, and your mission is just to discover what's out there.
All right, so let's put our engineer hats on for a minute. How do we actually do this? Well, it really boils down to an essential toolkit with three main techniques for taking all that raw, messy data and finally giving it some structure.
The first and maybe the most fundamental tool in the box is clustering. The goal here is pretty straightforward. Find the natural groups hiding in your data. It's kind of like when you walk into a party. You immediately see people forming little circles based on who they know or what they're talking about. Nobody tells them to do it. It just happens. The algorithm does the exact same thing, just with data points. And of course, an engineer has a whole bunch of different algorithms to choose from, because, well, not all data is shaped the same way. An algorithm like k-means is great if you already know you're looking for, say, 3 different types of customers. But for cybersecurity, something like dbScan is way more useful because it's fantastic at finding those dense clumps of normal activity and automatically isolating anything that looks weird or stands on its own.
And boom, that brings us right back to our cybersecurity problem. See, the real magic of clustering isn't just about finding the groups themselves. It's about defining what normal looks like. Once you've mapped out all these clusters of typical, everyday network traffic, anything that doesn't fit in, well, it suddenly sticks out like a sore thumb. It becomes an outlier and a potential threat that an engineer needs to look at right now.
The second tool in our kit is association. This is all about finding those hidden if this, then that rules in the data. The classic example always comes from retail. If a customer buys coffee, what's the chance they also grab some sugar? Finding those links lets you predict what might happen next.
And finally, our third tool is dimensionality reduction. I know it sounds super technical, but the idea is actually pretty simple. Modern data can have hundreds, even thousands of different features or variables. This tool helps us simplify all that mess by figuring out which variables are most important and just ignoring the rest of the noise. It's kind of like taking a complex 3D object, like a chair, and just looking at its 2D shadow. You've lost a dimension, but you can still easily tell what it is. That's what we're doing with data, stripping away complexity so we can see the real pattern.
So, we have our toolkit. But any good engineer will tell you, having great tools isn't enough. You need a process. Unsupervised learning isn't just magic. It's a methodical, 5-step blueprint for turning that raw data into something you can actually use.
And here's what that workflow looks like. First, you gather up all the raw unlabeled data. Then, and this is super important, you pick the right algorithm for the job you're trying to do. After that, you just let the model train. Let it go find those hidden patterns on its own, and once it's done its thing, you get to what is by far the most critical step of all, interpretation. This is where a human expert has to step in and figure out what it all means. A really good way to think about this whole process is to imagine you're organizing a giant, completely chaotic library. Step 1, gather all the books. Step 2, decide on your strategy. Are we sorting by author? By genre? That's your algorithm selection. Step 3 is the actual work of stacking the books. And then, finally, you walk through and put labels on the shelves. Fiction, history, science. That last part, that's interpretation.
Okay, so let's bring this all full circle. Let's go back to that original challenge. How does this toolkit and this 5-step blueprint actually stop that invisible cyber threat we talked about?
Right, so here's the absolute key takeaway. The system doesn't need a list of known viruses or hacks. It doesn't care. Using clustering, it just built an incredibly detailed picture of what normal network traffic is supposed to look like. It creates these really well-defined clusters of normal behavior. So now, any piece of data, any activity that falls outside of those normal clusters gets instantly flagged as an anomaly, and that's when a human security expert gets an alert. It finds the unknown simply by having a perfect understanding of the known.
Now look, as any engineer will tell you, no tool is perfect. The upsides here are massive. It works with raw data, it's efficient, and it can find patterns a human being might never spot. But the challenges are just as real. A model might create a perfect cluster of data points, but give you zero clue why those things belong together. That interpretation is still on us humans. And there's always a risk the model finds a brilliant-looking pattern that's actually just random noise, sending you on a wild goose chase.
And this analogy really nails the core challenge here. Using these tools is a lot like being the first person to explore an uninhabited planet. You are absolutely guaranteed to find some new, unique things, but you don't have a map. And without one, it's really easy to get excited about a random pile of rocks, thinking it's some ancient monument. Figuring out what's a real insight and what's just noise, that's the real skill.
Which brings us to the final, and honestly, the most critical piece of this whole system. A model can spit out a million different mathematical patterns, but at the end of the day, it takes one human expert, a single security analyst, or a market researcher, to look at that pattern and say, okay, that's a threat, or that's a huge opportunity, or nope, that's just nothing.
So I'll just leave you with this to chew on. As our machines get smarter and better at finding patterns all on their own, whose expertise is actually more important? The engineer who builds the model, or the domain expert who understands what its discoveries actually mean in the real world? It's something to think about. Thanks for joining me.